Okay, mathematicians, so now we're going to case number 3 of theorem 2, which is still the theorem angle at the center must be twice the angle at the circumference. Now it just looks a little bit different, and that's why it's got a little bit of a different proof. So it's a continuation of this theorem that we've just proven in the previous video, just a different case because it looks a little bit different. Just like before, we need to do constructions and create some exterior angles. So again, the construction is the same. We're going to have to go through A, through O, all the way to N. So construct AO, N. That was step number 1 in the previous proof as well. I hope you agree with it. So therefore, construct AON, where N is on the circumference. Okay. It's very vital that you do constructions in a test. If you don't show constructions or state the construction, we will not mark anything else. Okay, so from there we can start off now. So we want to prove this over here, but at the moment there's nothing that we can, no triangles that we can use that with exterior angles that's just got that angle over there. But if I work in this triangle OAB, I can see that this is an exterior angle, and we're going to call that O1. Okay, so OAB, if I work with that triangle, exterior angle will be O1. Okay, let's just make that interior angle there, A1 there. Okay, and then we go into the next one. If I work in triangle OAC, this whole angle over here will then be the exterior angle. Okay, and then we call that one O2. And in that triangle, we're also going to have to work with angle A, which we'll then just call A2. Okay, and from there, we're going to start. So let's start. We just stated that O1 is the exterior angle, so O1 equals to the sum of the opposite interior angles. So that is A1 plus B, because of exterior angles of a triangle, exterior angle of a triangle. Okay, and that looks similar to the previous two cases. So again, we're going to have to go and say OB and OA is equal. Why? Because that's from the center to the circumference, from the center to the circumference, which makes it radius. So OA equals to OB because of radii. Therefore, we know that angle A1 equals to B. Angles opposite equal angles. Angles opposite equal sides, sorry. That's the same as saying isosceles triangle. From there, we can now just substitute. Instead of B, we're going to write A again. So therefore, O1 equals to A1 plus A1. So therefore, O1 equals to twice A1. And that looks very similar to the previous case that we've proven, but now it gets a little bit different later on. So let's go on. So we spoke about this whole angle over here being the exterior angle of OAC. Just like the previous one, we're not going to prove that whole thing. We're just going to say, similarly, O2 will be equal to twice of A2. Okay. But now our problem comes. So O2 is this whole angle over here, and O1 is just this small part over here. So if I want to just get that angle over there that's inside the angle, I have to take the whole angle and subtract O1. So BOC will then actually be equal to O2 minus O1. And that's where I'm going to start. So O2 minus O1 will then be equal to 2A2 minus 2A1. And we've just said that if I subtract those two, I get angle BOC, what I want to prove. And then I'm going to take out the common factor in the other side. So that will be A2 angle minus angle A1. And if I go look at that, so it's that whole angle over there minus A1. So the only piece that is left is this angle BAC. So therefore, that will be 2BAC. And that's the proof done. Well done. Thank you.